Okay, so let's keep talking about Eulerian stuff. So, yeah, we just proved theorem 5.1, which is about Eulerian circuits, and a graph has an Eulerian circuit. Well, okay, let me state it properly. Let G be non-trivial and connected, then G has an Eulerian circuit if and only if every vertex has even degree. Now we have a theorem about Eulerian trails. Keep in mind that an Eulerian trail, it uses every edge exactly once, and it is not closed, meaning that the start and the start and end vertex are different. So here's the big theorem about Eulerian trails. So first, let's assume that G is connected. Then G has an Eulerian trail if and only if there's exactly two vertices of odd degree, meaning that all the rest of the vertices would have even degree. And to prove this, there's kind of a simple yeah, so I'll just doodle on the bottom of this, but there's a really simple trick. Roughly speaking, an Eulerian trail in a graph say I just drew a graph with an Eulerian trail. If I have an Eulerian trail, then I can make a new graph with an Eulerian circuit by just adding a new vertex, and the new vertex is going to have degree 2, and its two neighbors are going to be the starting vertex of the trail and the ending vertex of the trail. So, okay, so let me cover this back up with my hand. And so the original graph had an Eulerian trail, starting here and ending here, and it went like that. Wait, here, 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 here. And then the new graph is going to have a circuit, and I know that it has a circuit basically because I can just start here, I can follow the same trail that I had before, and then I'm going to end up here, and then I'll just go here, and then here, and then I will have ended up back where I started. That's what this new vertex of degree 2 gives you. We already had a way of getting from here to here and using every edge. And then I drew two new edges, and then I'm going to use this one and then use this one. And I make an Eulerian circuit in the new graph. So the original graph has an Eulerian trail if and only if the new graph has an Eulerian circuit. And we already proved a nice theorem about Eulerian circuits last time. So that's basically what we're going to use for this proof. So let me go over it more formally now that I've gone over the basic idea. So this is a two-directional thing. It's an if and only if statement, so let's prove the two directions separately. So let's prove the forward direction. So I'm going to assume that, well, I didn't write it, but I'm assuming that G's connected. I'm not really going to use that for this part, but formally we're assuming that G's connected, and we're assuming that G has an Eulerian trail, and then we have to prove that G has exactly two vertices of odd degree. So suppose that, and so suppose that G has the Eulerian trail, and just to nail things down, we will spell out like what is the trail. It starts at V0 and ends at VL. And this is a trail, an Eulerian trail, so V0 and VL are not the same. And then I'm going to basically formally do what I informally described just a second ago. I'm going to make a new graph. I'm going to call it G prime. It's going to consist of G, and then this notation means that I'm going to add a new vertex And then I'm going to add an edge from W to V naught, and also an edge from W to VL, which is really just what, I mean, that's really what I drew in this picture. Then G prime has the following Eulerian circuit, and like I was describing, that this is the same Eulerian circuit that I described. You start at V naught, you go to VL, and then you go to W because there's an edge from W to VL, or, well, from VL to W, but we don't have directions on our edges. You can go from W to VL, or you can go from VL to W. So we go from VL to W, and then we go from W to V naught, and so then we have started and ended at the same spot, and that's an Eulerian circuit. And what do we know about graphs with Eulerian circuits? They have vertices. All the vertices have even degree. So in G prime, this new graph that we formed, we know all the vertices have even degree. And what we're supposed to show is that in the original graph, G, all the vertices have even degree except for two of them, which have odd degree. But to conclude that, we just have to think about what did we do to G in order to get G prime. Again, all we did was it's like in the picture, here's G, and then here's G prime. All we did is we added a new vertex with two neighbors. And we're saying that in this graph, all the vertices have even degree. So then we can just imagine what would we do to get the original graph G back. I would remove this. So we get rid of a vertex, and then VL is going to have the new degree if I remove this vertex again. VL is now going to have odd degree because it had even degree before, and then I remove an edge, and so then it's going to have odd degree. And same for V naught. The rest of the vertices aren't going to be affected when I remove W. W only has two neighbors, this one and this one. So basically that's what I said. In the original graph G, all the vertices have the same degree that they had in G prime, except V naught and VL, and those degrees get decreased by 1. So in the original graph G, V naught and VL were the two vertices that had odd degree. And there's two of them, they have odd degree, all the rest have even degree. And that's what we wanted to show. All right, what's the other direction? So once again, we're universally assuming that G is connected. But now I'm proving the reverse direction of this, meaning that I'm going to assume on top of the fact that G is connected, I'm going to assume that G has exactly two vertices of odd degree. And then my job is to show that G has an Eulerian trail. So, and I'm going to use the same idea. The idea is basically just that the two vertices that have odd degree have to be the start vertex and the end vertex for an Eulerian trail. So suppose that G is connected and has exactly two vertices of odd degree. Then I'm going to make my G prime again. I'm going to make G prime by adding a new vertex, and I'm going to make it adjacent to this and this. The new graph has all even degrees, right? Because, so what just happened? I added a new vertex, and from the new vertex, I drew edges to two neighbors. So the new vertex is going to have degree 2. That's even, so that's good. The degree of U gets bumped up by 1 because we drew this edge to U. And so the degree of U was odd, but now it's going to be even in G prime. The degree of V was also odd in G, but will be even in G prime. So in G prime, all the vertices have even degree. Right, G prime is also non-trivial and connected because it doesn't just have one vertex. Like we already started with at least two vertices and then we added one. So there's definitely, it's not a trivial graph. A trivial graph has just one vertex. And it's also connected because G was connected, right? So G prime has an Eulerian circuit. It satisfies all of the requirements of theorem 5.1. It's a non-trivial graph and it's connected and all the vertices have even degree, so it must have an Eulerian circuit. So G prime has an Eulerian circuit, and like I was saying before about Eulerian circuits, the starting point and the ending point are sort of arbitrary. If you have an Eulerian circuit, you can easily turn any vertex into the starting point. Just start there, follow the Eulerian circuit until you get to the end, and then go back to the beginning and come back and follow that until you're back to where you started. So if there's an Eulerian circuit, we can basically regard whatever we want as the starting vertex and ending vertex, and I'm going to choose W. I'm going to say that this is an Eulerian circuit that starts and ends at W. So W is V naught, and W is also VL. But then, yeah, let me point back to this picture. We have this Eulerian circuit of this graph, and then if I remove W, what I get is an Eulerian trail, because basically what I have to start with is an Eulerian circuit that starts and ends at W. And this must, like if it's starting at W, then the next vertex could, I guess, be either this one or this one. But it goes around until it reaches the other one, and then it goes back to W. But if I just skipped the very beginning and the very end, what I would have is an Eulerian trail that starts at one of these and ends at the other one. And that's all I'm going to say. So yeah, I just take this, but I remove the beginning vertex and the end vertex because those are that's W. And what I have left is an Eulerian trail of the original graph G. So that's the proof.